So hello again. Tonight we're going to talk about space mining, and you probably have heard various aspects of that. We're going to define the scope of what the presentation is going to be about. Most people are aware that, we go out to places and gather samples, the moon, asteroids, things like that, comet tails, and bring the stuff back. But we're looking for, elemental signs of life or flowing water, those kind of things. We're not looking for, as the saying goes, the good stuff, the stuff that's going to make lots of revenue. But NASA will occasionally point out things that are going to make more revenue. The kinds of things you can go out into space and maybe make some revenue on are minerals, compounds mixed with other things, or just mixtures of different materials that aren't actually made into compounds. Same with gases. You can find mixtures and compounds of gases and liquids. You can find all sorts of stuff. But we're going to narrow our focus on not, going and finding gold and platinum or diamond rain gemstones. We're going to focus on the actual trying to decide whether space mining actually makes sense from a financial and business and operational perspective. So we'll get into the minutia, which is what we're known for. So what would be the intent on doing this? Well, obviously, it's about the Benjamins. If it's not NASA, it's going to be about the Benjamins, either for providing the service to somebody else or for going out there and getting stuff and bringing it back for revenue. But why would you want to go to space to get something? Well, if something is predominantly only found out there, like the element iridium is, Earth is very iridium poor. Actually, we have a lot of iridium. It's just a dense material that has sunk closer to the core of the planet. Therefore, there's no easy to get at iridium near the surface, except in a certain layer where the dinosaurs bid goodbye. But that's thin. You could also be going for things that are limited or scarce on Earth, like gold or platinum or diamonds, stuff that's worth something. We'll get into whether it's profitable to do that or not. Or just, once we consume everything that's here, we may have to go elsewhere because the Earth's not making enough of it anymore to compensate for how much we're drawing out of it, like, natural gas for burning stuff or for chemical industry, helium for a number of different things, or just potable water. If you've ever watched Helen's presentation regarding the amount of water that's available for us to drink and use in industry, it's a percentage-wise small amount. Not every drop in the ocean is usable. Or, somebody could go out there, spend the billions and change something that's scarce into something that's abundant, only available from them. So, they're going to go out and find something, make it cheap by dumping it in the market, and that will make them a monopoly. And so the other companies will fall by the wayside. And the company that spent the money to bring it back and took it from scarce to abundant is now your sole provider, and whatever price you name is how much people are going to be willing to buy. It's kind of like how it is in the battery market, with where you're going to get your lithium or your other metals from. Is whoever can provide it in the highest volume at the cheapest price is going to be dominant. So that may be why you're going to go get something from space, not because there isn't already an amount of it already here on Earth. It's scarce enough on Earth that if you bring back and make it abundant, you basically make a monopoly. Some of you may have heard of the term dry hole, and that refers to when they would drill for oil back in the early days, they were just giving it a try. Try here. I think we have a well over there. Try here. It's probably good. And then they would drill down a couple of thousand feet and not find any oil. They might find natural gas or helium or all sorts of things, but they didn't find any oil. So where they drilled was referred to as a dry hole. And that meant they spent a lot of money drilling down there and got nothing in return for it. Over the years, they've improved the technology for finding what's under the ground before you start drilling for it. All sorts of instruments for doing that. But what they found out was when you drill down and you find something, it may not be actually that large, a reserve of it. It could be just a bulge or a pool. The rest of the vein containing that material was very thin. So, it's a matter of the business. You can find that, you tap in somewhere that looks good and you find out it only lasts for a few years. and then you get very little back. So even though it's not a dry hole, it's a minimum return on investment. So if you're going to do that off in space and it costs billions of dollars to get the stuff out there, you want to make sure you don't come away with any, hey, we thought we're going to go there and get lots of platinum, and the amount of platinum was so small it wasn't worth the cost of the rocket to get there. So identifying what's going to be a good return versus a dry hole is something they have to research and figure out. So how do you identify sources? Let's say on Earth, if it's on the surface of the Earth or in a cave or underneath the seafloor, we have means of scratching the surface, digging below the surface, exposing close to the surface veins of material, and then just scraping it up from there. Or we can drill holes in the ground, coring for samples, and see how deep it is. And if you actually start a pilot drill well, then oil can come up under pressure, or natural gas, or even helium. But we've advanced the technology for identifying through the ground whether stuff is down there based upon analysis, typically spectroscopic analysis. So we're looking at waveforms of things, either transmissive through the ground or reflective off of it. So we're looking at radar, either on the ground penetrating radar, or from space, probes in space that do synthetic aperture radar across an area, and they look at the spectral analysis of it and decide whether or not there's gold or platinum or silver or whatever down there. And we can also look at it from space. So when the sun is shining on an area of ground that has lots of metal in it, the ground will be hotter. One of the ways that they discover, let's say in Egypt, if there's any underground vaults, is they actually let meson particulates pass through the earth, and then they catch them on the surface of the earth, and that way they can image caverns underground. But they're trying to do the chemical analysis and find out what's down there and how much of it's there, and is it worth actually doing that. And so that's improved the profitability of mining and drilling operations on Earth. But you have to have proximity to whatever your target is in order to do that level of testing to give you an improved assessment of whether or not it's profitable to do that. And in space, going out somewhere only to find out, nope, there isn't anything that we thought was going to be there, or there's some there, but very little of it. Well, you've already spent, better part of $1 billion to get you there to find out there's nothing there. So you have to find out what the return on investment will be for wherever you're going to go and get stuff. The top billing items that you would see as possible places are asteroids and comets. So you'll see a lot of things like asteroid mining or comet mining, or when they talk about space mining, it's asteroids and comets. And okay, that's a really wide selection because there's many tens of thousands of those sorts of things. So if we wanted to narrow it down, first, can we include some other stuff? Yes, beyond asteroids and comets, the moons of the planets in the solar system have already been recognized as having stuff. Like Titan has a lot of natural gas, Titan being a moon of Saturn, already has lots of natural gas on it. In fact, it's so compressed, it forms liquid lakes of natural gas. Now, why doesn't it go boom? There's not enough oxygen in the atmosphere to make it combust, even though there's lightning from static electricity, which I think is amazing. You can have lightning that will strike a liquid pool of natural gas, and there's no explosive result because there's not enough oxygen in the atmosphere to do anything about it. But Jupiter and Saturn, their atmospheres both have helium in them, so you could get lots of it from there, but you have to be in orbit, close proximity to the atmosphere without the gravity sucking you in. And there's always what NASA mentioned a while back during the Voyager missions, that they postulated that because of the chemicals and the pressure and the temperature, the planet Neptune may actually have diamond rain. The carbon-based materials are falling out of the sky because of the cycling, and they're under such pressure that the carbon will form microscopic grains of diamond. And if you want a real easy way to get tonnage of diamond, just go into the upper atmosphere of Neptune and scoop out some. So people will think, I can go get diamond. Yes, but these are microscopic diamonds. You're not going to put this on anybody's ring finger anytime soon. But what you might use them for is in industrial processes on Earth. Like if you want to draw out wire to a very small diameter, you use a piece of diamond that has a very tiny hole through it. And then you, under great pressure, pull the softened metal through the wire die. So let's say you've got this collection of targets and you want to find out which one makes the most sense, even before you evaluate what materials it has. Well, the first thing you want to do is say, well, I don't want to travel a long distance. I don't want to have to fly for 5 or 10 years only to find that there's nothing there. I need someplace closer. And if it's a shorter distance to it, it means a smaller rocket, which is reducing costs. So there's less fuel for liftoff or landing, or if we want to return materials that we've mined up, cost less if you're going to go a shorter distance. It also takes a shorter amount of time to get there and get back, which is better for human beings that you might want to be the miners. And you want to target that as a better opportunity for liftoff and return. So if where you want to go is Mars, you don't have to wait 2 years for the planets to line up. You fly there in 2 years, and then you have to wait 2 years before you can start to come back, and then it takes 2 years to get back. So you want to think about that. A shorter trip means if there's humans on board, they need less consumables, air, water, food, those kind of things. A lighter liftoff weight also means cheaper flight, and it also means that if you're carrying less at a lower speed back into the Earth's atmosphere, it's an easier return to the surface with whatever you're bringing back. So let's think about comets for a moment. Would it make sense for us to go get stuff from comets or gather it from the tails of comets? Turns out comets are not a good thing to do mining with. The long orbit, long period comets that come out from like the Oort cloud, those can take a long time to get around the sun. They are repeatable. Halley's comet's like 70 some odd years, but if you launch to it, you have to wait about half that length before it'll come back close enough for you to lift off from the Earth to get there. And then once you arrive there, you have to wait for it to go around the sun and come back close to the Earth again, which could be 5+ years. That's not practical for human-operated mining. What about these shorter duration comets, the ones that don't make it all the way out to the Oort cloud, that maybe only make it as far as Jupiter and then back to the sun and then back again? It's a shorter duration. You still have to wait for it to swing around the sun, but it's certainly shorter than the long duration ones. But it's not practical for humans to do that because it's going to swing around the sun in close proximity. And some of these short duration comets are one-timers. They may look profitable, but as it swings around the sun, it's not far enough away from the sun, so it crashes into the sun, no more comet. If you're going to use that as a source for your mining, you want to make sure you get multiple trips. So a short duration comet that may or may not be a one-time, the return on investment's not good enough because you'll always be in search for new sources if a good percentage of them are one-timers. What about the asteroid belt? Lots of asteroids in the asteroid belt. That's true. And they're not like they are in science fiction movies. The asteroids are not like, within 50 feet of each other zooming around. There is actually many miles between them. And so if you wanted to move from asteroid to asteroid, it takes propulsive force. So carry a large gas tank or run an ion engine that's good for about 5 years. But the biggest of the asteroids, Ceres, Pallas, Vesta, Juno, those kinds of things, there's a lot of distance between them. There's millions of miles between them because they're in different parts of the orbit of the asteroid belt. So that's going to take you a while to get there. And if you pick one, it may take multiple years for you to get there. And then you may have to wait multiple years for it to come around again to be closer to the Earth because the asteroid belt is out beyond Mars before you get to Jupiter. Not impractical for human-based mining. You may have heard of NASA's Lucy mission. It's going to go to the Trojan and Greek asteroids that are in orbit around the sun with Jupiter. And the Trojans are at L5, Lagrange point 5, and the Greeks are at L4. So you can see from the diagram over on the right where it says L1, L2, that would be where Jupiter is, that little sphere. And then ahead of or behind in the same orbit, you have generically referred to as Trojan asteroids. Unfortunately, they're too close to Jupiter. It takes a while to get there. Lucy, I think, is going to take more than 2 years at high speed with a couple of gravitational slingshots off the Earth and the Moon to get out there as soon as possible. Multiple years to get there, and then you have to wait an orbit of Jupiter. An orbit of Jupiter is multiple times the orbit of the Earth, so not good. So it would take even more energy to get back, even if you conserve the energy to get there. So that's not practical for human-based mining. Plus, Jupiter has an orbit that's filled with radiation belts because Jupiter is so massive and has an enormous magnetic field. You have a radiation field in the orbit of Jupiter, so not a good place. As I mentioned in the accidental meteor shower from last week, from that presentation, there's this thing called the Apollo and the Eten group of asteroids that are in orbit around the sun with the Earth, but the orbit centers are not the same. So these two groups of asteroids are a little offset. And for a certain number of months of the year, these asteroids are in proximity to the Earth. So that would mean it would be easier to get there, take less than 2 years to get there. And then once you get there, you'd have to wait at least a year before you could come back. So it's better, but that's not really good. And the people that want their money from their investment aren't going to want to wait that long. So again, not practical for human-based mining. But there's another set of Trojans. They shouldn't be called Trojans because they're around Earth, but Trojan-like asteroids because the Earth going around the sun has Lagrange points L4 and L5. They're smaller, but it would take less time to get there, take less than a year to get there probably. There's fewer of them. So your targets of opportunity may be less, but it's easier to get there. It's easier to get back. If you go to L5 as your target source, pick an asteroid around L5, and then when you want to come back, you just sort of hang into the orbit with Earth, give it a little bit of push so you're ahead of the orbital velocity, and you'll get back to Earth. If you want to come faster, you can, so you're like taking advantage of the orbital speed of Earth to get back. You could take the long way around. You could go to L4 and then just slow down until Earth catches up with you, but that actually takes longer. But that may be the quickest way to get to asteroids and assay them to see if there's something worth bringing back. But it might be a good approach to proving out the space mining business. All the launch costs, the getting there costs, the getting back costs, processing, whether or not you're supposed to do processing. Earth Trojans may be a good first target. So getting to the source and back with the goods. The rocket on the left, that's a Falcon Heavy. That's kind of the biggest thing that SpaceX has operationally now. And they'll take things to geosynchronous orbit. It'll also take things beyond the orbit, beyond Earth. And they've actually sent things to Mars using it. The very first thing that was launched was a Tesla Roadster. Didn't want to take a chance on launching a valuable payload, so they launched a car. But that's the size of the rocket when it leaves the Earth. What is the size of the capsule when it comes back to Earth? Well, the picture at the bottom is a Dragon cargo capsule. And you can see that it's quite a bit smaller. So let's say you wanted to go off to an Earth Trojan asteroid, mine a few tons of stuff, and then bring it back to Earth. They're very used to the Dragon cargo capsules carrying scientific instruments and stuff back to Earth from the International Space Station. So, it can deploy parachutes and land in the Atlantic Ocean, and you can get back maybe a ton of stuff. But if you want to go mine something that has a heavy weight, a ton is not enough to make it worth your while to do it. You need several tons. You're not going to get that with normal capsule. So the best way to reduce the weight of what you're bringing back is once you get out there and you mine it up, then the next thing you might want to think about is maybe if I do a little post-processing while I'm out there, then I don't have to bring back as much essentially dead weight. If you look at it on Earth, they'll mine rock, raw ore out of a particular location and then bring it back somewhere else for post-processing it into the mineral result. That way you only have to put the processing facility in one place and you can have several mines bringing the rock, bringing the ore to it. That's the same way that petroleum is processed. You can have lots of wells out there, but if you either through tanker trucks or railroad cars. You bring all of the raw petroleum back to a processing plant, you need fewer processing plants. But given that you'll be out in space and anything you bring back is dead weight coming back if it's not part of your finished goods, you might want to consider taking some processing equipment out there to just get rid of some of the stuff that you don't want to bring back because you have to pay for it to be brought back. So if you're on Earth and you want to take some raw minerals, you have to think about getting it back to Earth. But there are also expectations of the processing. So let's say we wanted to do processing out at an asteroid, things that you don't think about until maybe now that you need in order to do some of these post-processing activities is gravity. So if you're crushing up a rock and you've got some lighter weight material that's in with the rock and heavier stone, you can actually run it off the edge of a roller and the heavier stuff will fall sooner and the lighter stuff will be projected outward. So that's a process in mineral processing that allows them to very easily separate out heavier stuff from lighter stuff. If you're doing this at an asteroid out in space, obviously you don't have enough gravity to do that. You have to come up with an alternative mechanism. On Earth, a lot of times when you want to separate out materials, and this is typically within radioactive material processing, you do what is known as flushing or centrifugal activity, centrifuges. And the idea is you can grind this stuff up, and then if you spin the centrifuge at a certain speed and you mix it in with liquids like water or acids, you can separate out the good stuff from the large volume of stuff that's just waste. Where are you going to get your water from? Well, if you happen to be lucky enough to be on an asteroid that has lots of water, you still have to go get it because where you're mining may be 100 miles away from where you're going to get the water from. So the water you use, though, can't be contaminated by local minerals. It has to be what is known as potable water. That's, not distilled, but it's close to good filtered, drinkable water as you can get, because that's what the industrial process works best with. How about something as simple as air? When you're taking rock and you're crushing it up and you want to get the good metals out of it, then you can heat the rock and the metals will become molten at a lower temperature than the rock. And so it's easy to separate them out. But that requires you to heat it to, over 1,000 degrees. And where are you going to get the fuel for the heating and the air? What if your asteroid has no atmosphere? There's no air. What if your asteroid doesn't have, like natural gas lakes? You got to bring the fuel for running the heater. So these are things you have to think about if you want to do your lightweight post-processing out at the source rather than bringing all the heavy stuff with all the spoilage back to Earth. So when you mine stuff, you don't get the good stuff directly. You can't stick a straw in the ground and suck out gasoline. You stick a straw in the ground, you suck out vaporous gases, liquids that you want, liquids that you don't want, and then you have to separate it all out. And sometimes the stuff you separate out, either in petroleum or in ore, is useful. So when you're going to get the platinum, you might also get some silver with it. Okay, that's good. But if you're going to get the gold and you get lead with it or arsenic with it, you don't really want that, but it comes along for the ride. So you have to go to the effort to separate it out. Maybe you can sell it on the side as a low profit item, but you may also wind up that being toxic spoilage of whatever your process is. And now you've got to pay to get rid of it because otherwise, some government agency may come and say, we're the EPA, you need to shut this down because what you're producing is unhealthy. So whenever they separate out this stuff, they have to deal with it. And that's a cost of doing business, which is negative to the return on investment. So when you do this out in space, there may be the corporate incentive to, we're going to separate out the toxic stuff and leave it on the asteroid. Well, before you got there and started mining it, the degree of toxicity of the asteroid was relatively low. But once you took out all the good stuff and you left the toxic stuff, the degree of toxicity of the asteroid goes up. If for whatever reason, that asteroid now takes a different course, a different trajectory, and either creates a toxic plume, a tail, or starts heading for Earth or Mars, you may not want the radioactive isotope garbage asteroid coming back into Earth's atmosphere. So you have to think about not just toxic stuff on Earth from mining post-processing, but toxic stuff in space. When the rocket takes off, it's expected to take off with whatever you need while you're out there. And when it comes back, it's expected to come back with, if there's people on board, obviously the people safely, but whatever your mined materials are. But you're also going to lift off and land with lots of stuff that the people might need. It might make sense to ship the machinery first, the mining machinery, the post-processing machinery first, and then ship the people. But that's added cost for the return on investment. So that's probably going to be a no-go on that. If you've watched some of the recent NASA missions to deep space, they're hybrid propulsion. So when they leave the Earth, they're using solid or liquid fuel to get that good boost to go off to another place. But once they get into space, they switch over to ion or Hall effect propulsion, which is highly efficient for long duration space travel. The actual speed that they can produce is low, but they can run for 8 months at a time. So the speed just gradually builds up until you get close to your destination. But as you get close to your destination, you got to switch back over to the liquid fuel to do your landing or take off from that target because ion's just not got enough oomph to do that. So you might want to examine the NASA OSIRIS-REx mission, which was a sample return from the asteroid Bennu. And Bennu is one of those asteroids in Earth orbit. So easy to get to, easy to come back to Earth with samples. But that was a liquid fuel on launch, ion to get there, and then they needed some regular liquid fuel to get things back, descend into Earth orbit, and then return the sample. The actual OSIRIS-REx capsule continued on to another asteroid. So it just did a drop-off. So if part of the fuel that you need to take your ship out there is the fuel necessary to land at the source and then take off again, maybe you don't need to do that. Maybe you can use sort of a set of impactors that you carry kind of like shotgun shells, and you blow materials off the asteroid, or you take a laser along that's solar powered and you use it to blow off materials from the asteroid, and then you scoop those up on orbit with the asteroid, making sure that you don't send any directly counter to your direction of travel, which might damage your craft. But you collect the materials in orbit without ever needing to land and then take off. And you post-process it all in orbit. That also means that your crew capsule, your crew along with the machinery can get there. You do your standoff mining, do your processing, pull the contents back into your departure capsule, and then the astronauts and the good stuff comes back to Earth, and you leave the mining equipment in orbit. So you can send a capsule back the next time that's empty and do the mining again. So you have some reusability of the capsule, and you have reusability of the mining and the post-processing equipment. You might need to bring some more shotgun shells, so to speak, to do more impactors. But if you're using a laser, all you need is sunlight. So that reduces your costs for multiple trips. Assuming that the asteroid you pick is well endowed with whatever minerals you're going after. Reusability is always a plus factor in your return on investment. Now, if you've looked at the OSIRIS-REx and the Lucy missions, you might think, what's NASA doing this for? Why do they care about what materials are in asteroids? Well, scratch below the surface and what you'll find out is big corporations saying, hey, NASA, could you take some of that taxpayer funding you get and send a mission off to over here and see if there's any good minerals there that we might want to go get in the future, but we're not going to spend our dime to go out there and find a dry well. So, yeah, some of these return missions and assay missions are really in disguise. Hey, U.S. Metallurgical industry, there be platinum over there, or there be natural gas on Titan. But it makes sense that this is how we work, so to speak, that the highly riskful, highly jeopardized return on investment is done by taxpayers as opposed to corporations coming in and going bust quickly. But if you think about it for a moment, what you'll uncover is who can make more money than the mining? Well, in order to do the mining, you're going to need rockets. You're going to need space capsules. You're going to need spacesuits. You're going to need a company that knows how to deal with like stony materials, how to navigate in space, how to get things out there, maybe to have batteries that last a long time, solar panels. You need all this stuff. But my guess is that's the first company that's going to make a lot of money off of space mining is not the company that's doing the mining, because they're going to come away with dry holes probably too often to make it profitable for the initial companies. They're going to have too many things they didn't think about that suddenly cost, $500 million, and they're going to go bust quickly until they get it right. What company can you think of that knows how to do all these things already? Well, that would be Tesla and SpaceX. Tesla knows how to do energy storage, Optimus robots. SpaceX knows how to do rockets and capsules and spacesuits. And the Boring Company knows how to cut through dense rock materials. So any company that's prepared to be the first one that makes a small fortune off of space mining is likely to be the companies that Musk has investments in. I don't know if it's on purpose, but it certainly seems to be, as the saying goes, coincidental. But maybe it doesn't make sense for people to do the mining. Let's say we train some autonomous robots to do the mining for us. So now it doesn't matter if it takes 2 months or 2 years to get out to the target. It doesn't matter if it takes 2 months or 2 years to get back. The robot's not going to care. In fact, it might even be advantageous to take a bunch of robots out there with the mining equipment and have the ship come back autonomously and leave the robots out there. So if you think about it with humans, you send the humans out there, they do mining for a certain period of time, they stop mining, they get back in the capsule, they come home. That's a lot of dead mining time. If you send the robots out there, they do the mining. When your capsule's full, they send the craft back with no body on board, no robots on board. And in the meantime, the robots continue to do mining. And then now you send an empty capsule back up sooner, and you have stuff to put in the capsule right away. And then you send it back. So you can create kind of a bucket brigade and be a lot more profitable because every flight can carry back sooner because the robots are still mining. By the way, what company has the robots that could do this? Tesla. So in conclusion, mining in space is not as simple as first blush thought. You don't just go out there and get the rock and come back. It makes sense to use tax dollars for initial resource exploration. Otherwise, the dry holes will kill off the industry. It makes some sense to do some amount of post-processing at the site in order to reduce the tonnage you need to bring back and land on Earth. Picking a proper source target helps with the mission. So let's start out with the asteroids that are already in Earth orbit. Those are easier to get to, easier to get back from. Using robots and leaving machinery at the site makes a lot of sense, just reusability and economically. This is going to be extremely resource consuming financially, billions at risk for dry holes, unexpected costs that nobody ever thought of. And what if it goes oopsie? Something can go wrong. And then you're out, $1 billion for a rocket launch. That's going to doom an industry really quickly. Unless it's a material only found in space in abundance, it's still far cheaper to mine things on Earth, even if it's deep under the ocean floor, than it is to ever consider mining them in space. Spend the dollars here, plan for what you're going to do in the future, and if you ever really run short of some resource, watch this video once I post it on YouTube first. And as usual, links to stuff. So, comments, questions, things I didn't think about, nuances?
So instead of bringing it back to Earth, wouldn't they be more likely to bring it to some automated construction site on the moon or somewhere else so that they don't incur the extra expense of getting it in Earth's gravity, bring it there, and then use it for further space exploration?
Well, if we're building colonies on Mars and on the moon, then it makes sense to bring the resources back to those locations rather than bringing it back to Earth and then taking it back up. Yep, that does make sense. But as a stop off point, if you said, I'm going to go to an Earth orbiting asteroid, get the materials, and then bring them back to the moon instead of bringing them back to the Earth, if you looked at the Lagrange points, L4 and L5, it's actually easier to get back to the Earth than it is to get from L4 and L5 to the moon, because you don't have to take into account two orbiting things, just one. But the moon has lower gravity, so it's easier to land there. But you have to use propulsive force to change your orbital trajectory from the Earth orbiting L4, L5 out to the moon. But yes, it's good thinking. If we ever have encampments on the moon and Mars, why send it back to Earth to have it processed only to send it back up? Send it to where it's needed.
Hmm. Yeah.
Okay.
Let's say you brought back a whole bunch of diamonds. Wouldn't that radically change the economy?
Yes, that's in one of the early slides. If you said, I'm going to get diamonds in tonnage and it's going to obliterate the diamond market, so diamonds will no longer be scarce. Let's say I bring back big diamonds, like diamonds that are worthy of becoming jewelry or pendants or whatever. Then who do you think is going to want to stop you? It's a company called De Beers, and this has happened before. General Electric Corporation found that they could make good quality 2-carat diamonds in an industrial furnace, and they could make them in quantity. Because, once you build the furnace itself doesn't take up that much space. It's just a round cask thing that you put lots of electricity in to heat it up. And you just leave it in there for a while under massive pressure, and out comes chunks of diamond. So when De Beers was told this by GE and De Beers got into a situation because GE was about to, not only for the industrial market, but for the jewelry market, just basically destroy the market for De Beers. And so let's just say rumor has it that some funding exchanged hands. And so GE would not enter the jewelry market, and De Beers would always provide kind of a flat price for the jewelry market that's got a good margin on it. So yes, if you had a spoiler, go out and get lots of anything that's scarce on Earth and bring it back in tonnage and introduce it into the marketplace, it's going to wreak havoc on diamonds, gold, silver, platinum, any of those sorts of things. Now, can you stop them? I don't know. Maybe you can take them to U.S. Federal Trade Commission courts and say they're deliberately dumping in order to create a monopoly. But if you're deliberately dumping, you're going to lower the price. Therefore, the people that already are producing the goods that have an elevated price can drop their price to below what it's costing you, because their stuff they're getting out of the Earth cheaper than it's costing you, even in tonnage, to go out somewhere in space and bring it back. So I don't know. It's kind of like saying, if somebody ever invented a battery technology that was far better than lithium, far better, and cost far less and was a lot lighter, couldn't they just conquer the market? Chemistry only works certain ways. So until somebody comes up with, I don't know, a Casimir power module that doesn't require charging, the battery market is safe, even if somebody says, hey, I've got a sodium battery. It's kind of like a lithium battery, but we use sodium instead. Yes, sodium is about 20% cheaper than lithium right now, but sodium is plentiful. Lithium is less plentiful. So it's hard to dump like sodium batteries on the market because it's plentiful.
True. Huh.
Okay, any more comments or questions before I stop recording? Hearing nothing.